right, good afternoon, everyone. In the interest of time, I'll just go ahead and get started. I think we're going to have a great discussion, and I want to thank the previous panel. They did a wonderful job, too. I enjoyed that previous session. My name's Hanjiro Ambrose, and I'm a lead staff at the California Air Resources Board, working on building embodied carbon. And I'm a UC Davis alum. I did my doctorate here and my master's, so I'm excited to come back home for a minute and get to see a lot of familiar faces. So thanks for having me. So I'll start off really quick before I welcome our panel up and give a little information about work at the Air Resources Board with respect to reducing building embodied carbon. So in the last 2 years, the legislature passed 2 bills which created some broad authority and goals for the California Air Resources Board to develop a framework for measuring and then reducing the carbon intensity of building materials across the state. As part of these legislative mandates, it includes a target for a 40% net reduction in greenhouse gas emissions no later than 2035. So some pretty ambitious goals that we're currently looking to implement. So California has adopted a number of ambitious goals for reducing greenhouse gas emissions, and these trace back to landmark bills, Assembly Bill 32 and Senate Bill 32, which were signed in 2006. And recently, there has been direction from the legislature to develop strategies and approaches to reduce emissions affiliated with building materials and the built environment, which includes Senate Bill 596, the net zero emission strategy for the cement sector, which I believe one of my colleagues will be talking about at a later session. In general, just to ensure that these long-lived products and materials are selected based on low carbon aspirations. So I'll give a quick update. We're developing a team at CARB right now to implement the goals of AB 43. We have had 2 new sections created at CARB, and I'm the lead staff in one of those. And we're in the process of recruiting and staffing right now. So we're just building up this spring since we've started hiring in this direction. We're currently developing a reporting tool which aims to collect data on building materials and carbon intensities, as well as other data on construction activities statewide. We also have 2 research contracts currently underway, one with some colleagues from UC Santa Barbara and another one that's going to be starting here with some colleagues in the room. And we have additional research proposals and research needs that I'm going to highlight at the end for folks in the room. If you're interested, we have a lot of data gaps and needs we've already identified, and we're looking for partners to help address. And our interest in developing partnerships is probably broader than our research contracts and needs. We're really interested in engaging and building, developing broad partnerships with a number of stakeholders, including non-governmental organizations, academic partners, private sector firms in the space, architectural, design, structural engineering, as well as other groups that, standard setting groups and intergovernmental organizations. So my contact information will be here at the end, and I'll be around today. One of my colleagues is here today too, and please feel free to talk to us. Like I said, we're really interested in engaging more broadly with the sector as we develop our team and develop our approach at the Air Resources Board. So I threw a few research needs up here, and I think these slides are going to go out to folks, and so I thought, this is one of those things that I think is fun to tee up at a conference or a symposium like this, knowing that there's a lot of academics in the room. I think we added a few here and the font got a little small, I apologize. There's a number of research gaps that we've been thinking about. I think, focusing in, I just think, we're really interested in building a better understanding of the costs and capacities of bringing on more supply of low carbon building materials. I've heard a lot of talks discussing actually what the costs are of bringing on additional supply of low carbon building materials. I think there's a lot of room for that. We're definitely trying to get a better idea always of the quantity of materials that goes into buildings, in addition to the types and archetypes of buildings out there. And we've been meeting with a number of the our sister agencies, as well as some of the national labs on their work, developing reference or prototype building models. So we're very interested in that work as well. So as I said, not a comprehensive or exhaustive list, but hopefully some ideas for folks to take back and tee up. As I said, we are going to be actively developing additional research contracts. And so I think these are some of those areas of needs that we're really interested in. So I'll go ahead. There's my contact information if folks want it. And also, like I said, I'll be around today. Please feel free to grab me. I'm going to go ahead and introduce our panelists. I'm really excited to discuss with them and lead this discussion a little bit. So our first panelist, Anish Tilak, is a manager at Rocky Mountain Institute's Carbon-Free Buildings program, where he manages the Embodied Carbon Initiative. Anish has a depth of industry experience and has a current focus on policy research and market development in low-carbon building materials. So thank you, Anish. I'll just go ahead and keep going. Patrick Cunningham is a PhD candidate at UC Davis and a grantee of a recent National Center for Sustainable Transportation dissertation grant. His work is focused on the environmental impacts of concrete and other cement-based materials. He has investigated bio-derived polymers as a Fulbright awardee and is particularly interested in how technology is shifting across industries and how industrial symbiotic relationships will shape the future. I think as somebody who's done a lot of work in industrial ecology, that's a very interesting area for me too. Jin Fan is a postdoctoral scholar in civil engineering here at UC Davis. His focus on the built environment, life cycle assessment, and sustainable design, also in reinforced concrete structures. Thank you very much, Dr. Fan, for joining us. John Harvey is a distinguished professor of civil and environmental engineering at UC Davis and obviously the director of the UC Pavement Research Center. I think we all know John and his work, I'm sure, or at least most of us do. Thank you, John, for taking part in our panel. And finally, Thomas Hendrickson from Lawrence Berkeley National Labs is the Energy Environmental Policy Project Scientist. He's a lead modeler, a project manager. He specializes in life cycle assessment and material flow analyses, techno-economic analyses, all the tools that we love to use in this room. Tommy holds a PhD and a master's in civil engineering from UC Berkeley. I want to just take a moment. Let's welcome our panelists. Thank you very much for joining us. And I think each one is just going to give a short talk to introduce themselves, and then we'll have some rounds of discussion and questions. So we'll start with Anish, please.
Thanks, everybody, for being here today. My name is Anish Tilak. I'm a manager in the Carbon-Free Buildings program at RMI, or Rocky Mountain Institute. If you're not familiar with RMI, we're a nonprofit organization. Our mission is to support economy-wide decarbonization. And I work in our Carbon-Free Buildings program in our Embodied Carbon Initiative. So what are we trying to do in our work? We're trying to create policy and market mechanisms that create demand for low-carbon building materials. So at this Industrial Decarbonization Symposium, we're hearing about the production side of the house, which is really how we decarbonize processes to create low-carbon materials, and I'll be talking a little bit about how we create demand for those products and really put marry that demand with the supply. So I'll just have a few slides to share just to frame the problem for everybody. What are we trying to do? We're trying to establish confidence in a set of new materials and practices in the construction industry, which is where I come from. My background is in architecture. The industry is a bit conservative. There's a lot of inertia that's preventing change and adopting new practices and technologies. So the first thing we have to do is just get folks comfortable and confident in using new materials and processes. The second is spurring efficient use of materials. There's a lot of waste that's going on in the construction industry today in terms of the amount of materials we're using. So we need to create ways to make materials used more efficiently. And the third is just to broadly create demand for low carbon materials that will be coming out of plants, industrial plants. So I'll just walk through how we look at this at RMI from a policy and market development framework. When we're talking about that first category, which is emerging solutions, how do we get people comfortable, confident in new technologies? It's about demonstration projects. So how can we support pilot projects either in the public sector or in the private sector? Testing labs funding to support testing of new materials that meet industry standards for what can be applied in construction projects. And then the third is how do we tie this to economic and business development, so actually creating good paying jobs in our communities. The second piece is once we get those emerging technologies out there, and then we consider them market ready, so to speak, and they can sort of flow into the construction supply chain, is how do we incentivize folks to use them? Because potentially they might cost a little bit more, or you might need a little bit more administrative work to actually apply those materials in projects. So incentives such as performance bonuses to contractors who use low carbon building materials is an option, financial grants to use new materials. For a policymaker who's at a local jurisdiction, like a city or township, you can use planning or zoning incentives as ways to reward developers who use low carbon building materials, give them a kind of streamlined pathway to permitting their projects. So those are just some incentives to accelerate adoption of these technologies. And then that leads to the mass market. So we've gone from carrots, which are the incentives, to sticks or codes and standards. And that's how we're gonna actually start requiring folks to use low carbon materials. And that's really the sort of long game in all of this, is to how does this work its way into regulation? But we can't jump straight to that third piece, right? Because the market's not going to be ready to adopt low carbon building materials and be required to do so. So you work your way through this framework, and once you get to the mass market, it's really about integrating low carbon building materials into building codes, public procurement standards. So there is a policy called Buy Clean, which essentially uses the purchasing power of government to buy low carbon building materials. So we have that in California. California building projects, public building projects have to meet a set of emission standards for building materials in key categories like steel, concrete, et cetera. And then we also have this at the federal level. There's a federal Buy Clean initiative going on as well. And then the last piece is building codes. So that covers everybody. So any developer who's building any building project ultimately has to go through a permitting process at their local jurisdiction, and incorporating requirements around building materials and low carbon building materials is starting to happen. And we have that here in California through the California Green Building Code, which we can discuss in the panel. But I'll leave it there at that kind of overview of how we look at creating a market through policy and different incentive options. And I'll skip through all the rest of my slides because I don't want to take up too much time. And I'll pass it to Patrick.
So I'll do my best to stand in front of the mic. I move around a lot and I use my hands a lot. But I'm Patrick Cunningham. I work for Dr. Savvy Miller. And I mainly look at concrete and cement, but we try to apply industrial ecology perspectives and techniques to the work we do. And so I'm going to be talking about how we can mitigate these impacts throughout the life cycle. And I want to acknowledge a lot of this work is also Josephine Olson, who's in the crowd, and I'll point her out again at the end too, her work as well that I'm sharing today. And so really, really quickly, the opportunity we all know is the challenge is society needs buildings, they need infrastructure, we need housing, we need roads. We also need to reduce CO2 emissions to mitigate the worst effects of climate change. And that's why I'm going to talk to you today about this opportunity to mitigate some of these impacts through reducing our material demand and through better engineering. And so this is a very simplified plot that you can kind of see the green arrow. Going from raw materials to production, there's a design aspect, and to construction, use, and end of life is kind of the cycle we have right now. And this is a little oversimplified, but kind of ways I like to think about these is we have opportunities to reduce impacts or reduce consumption and reduce impacts that way. We can reduce impacts by potentially reusing, whether it's reusing elements or the material or the whole building. And then we also have some end-of-life options for material recovery and maybe even circling back into production. And today I'm going to really focus in on this kind of opportunity up at the top to reduce our initial demand for some of these processed materials. And this just shows that exactly is that by better mixture design, better member design, better system design, and different end-of-life strategies, we might be able to cause a reduction in how much Portland cement we're using, which is the main emitter of greenhouse gas in concretes. And so just starting on member design, I like to think of that first because as engineers, usually we design a column or beam to do something a particular thing, and we need a certain strength of concrete for that. And so that kind of dictates later on our mixtures. So I'll start there. And this is some work by Josephine that she looked at a couple different building codes, but I just pulled out the ACI codes for this. And this shows a column and a slab and different ways you can optimize under existing code. So not new code, not new risk. You know, your insurance company will be happy with this because you meet code. Ways you can optimize your column and slab design. So for the column design, you see that higher strength concrete, a higher compressive strength. We can minimize the rebar, and that helps reduce our impacts by almost, well, let's say half, about half. And the same with this slab is we minimize our compressive strength of our concrete because we have these tensile loads in our slab, and we have to increase our rebar a little bit. But it enables us to also kind of, our options across the spectrum here are the high end is about twice as much as the low end. And so you've designed your column, you've designed your beam, and hopefully as an engineer, you've given us a performance-based specification, not a prescriptive, use this much cement or use this mixture. And that gives us then an opportunity to design our mixtures. And this is a very simplified kind of some examples of mixtures that we've made in our lab. A control with 100% Portland cement, 30% ground blast furnace slag, a common admixture in concrete to reduce the cement content. Replacing the cement, 30% of it with a natural pozzolan. And then we also made some alkali activated materials just to compare what those impacts look like. So alkali activated materials have no Portland cement in them. And so SCM reduction, you get approximately the same rate of greenhouse gas reduction. And then alkali activated materials, it varies by the alkali activator, but you can really drive down those emissions quite significantly. But of course, we're engineers, we need the same performance. So when we incorporate that perspective, and that's just very simply shown here, just one way we can incorporate that perspective is looking at a comparison unit where we have compressive strength and impact. And you can see that even though we really drove down those greenhouse gas emissions in our alkali active materials, some of them didn't perform as strongly. And so there are ways to better optimize alkali active materials, and people have done really great work on that. But this is just to illustrate that that performance perspective is still really, really important when we're selecting materials. And just kind of bringing us back out, I'll take a step back out as I finish up. And if we want to then kind of incorporate all aspects of this life cycle perspective, you can see the 18% reduction is from optimizing your design. The 34% is from switching out your materials, doing better mixture design. And then if we also add on improving your cement manufacturing process, so using natural gas, using renewable energy when you can use electricity. And then also there's some service life elongation there, so reusing your structure in place. We can today, with today's technologies, if we pick those technologies, we can drive down 70+% of emissions from these materials. And so I think that's the challenge, and that's also kind of a great opportunity motivation that I'll leave you with today. And again, I want to acknowledge Josephine. Go talk to her today. She's here, and some of our sponsors of this work. And I'll call up Jin next.
So this morning, Dr. Sabi talked about general topics Dr. Sabi talked about the general aspects of life cycle assessment of materials. And here I'm going to present, dive a little bit more depth into the methods. So I'm going to present next quantitative method for material assessment. As we know, the life cycle assessment is the most common method to quantify the environmental impacts. However, the conventional process-based life cycle assessment is very data intensive. Sometimes those data are not available, especially for those novel materials or materials that are being re-engineered or redesigned to reduce the greenhouse gas emissions. To understand those impacts, the resources must be assessed and the interlinks across different industries must be quantified. The Sankey diagram we are looking at here shows the material consumption from some of the typical construction materials like concrete, carbon steel, gypsum board, brick, and glass. So what we want to do is we want to make sure those materials, the allocation of the impacts are considered but not ignored, but also not double counted. To overcome the data challenges in the conventional life cycle assessment method, a first principle approach, particularly for mineral-based materials, can simplify the data needs and also ensure that we focus on the core processes in the material production. The first principle-based approach will inform direct enthalpy of the enthalpy requirements and also consider the different stages in the material production. For example, we consider the mineral purity and the necessary stages like coring of the minerals and the energy demands in the reactions or the post-processing like the grinding. In addition, like the inherent energy efficiency also needs to be addressed so that we can account for the associated greenhouse gas emissions. Here are a few examples that showing like applying the first principle approach to characterize the greenhouse gas emissions from the process we currently use to produce like concrete, low carbon steel, gypsum board, brick, and glass. The left top figure we are looking at here is how we can identify the individual contributions of the greenhouse gas emission from the composites of the concrete, like the allied, bilite, all the way to the aggregate. And similarly, it can be applied to other materials. In addition to those methods, we also want to make sure we consider the uncertainties in our analysis. Methods can be formulated so that we can apply uncertainty analysis to estimate the greenhouse gas emissions in data poor environments. For example, we can consider the variabilities in the emissions and also justify the data quality, consider other uncertainties so that ultimately we can determine the cumulative uncertainty to identify either the greenhouse gas emissions or other possible carbon uptake pathways, especially in the data poor environments. Here is another concept we talked about is like the timing of the emission release or uptake can also have a significant impact on the cumulative radioactive forcing. And this is often overlooked. But for the dynamic model we applied, on the other hand, we can consider the the emission pauses from the manufacturing process or the delays of the life cycle aspects like the biomass cultivation or the potential decadal carbon storage in the long-lived building materials on cumulative radioactive forcing. So the figure we are looking at here shows two examples. One is concrete, another is cross-laminated timber. And so we need to think about alternative resources to drive carbon dioxide removal. We have various carbon dioxide pathways that for the materials that can be long-lived in the building environment. For example, like carbonization of the concrete, which in the category of carbon mineralization, or we have photosynthesis of the biomass, which can also be utilized in the built environment. And like one more material I want to bring up here is the plastic. This figure shows like various bio-based plastic production pathways. So together, this bio-based plastic can substitute roughly 80% of the current plastic market. This suggests a huge potential for the plastic market to become a carbon sink instead of a carbon burden. And this pretty much covers the materials I want to present today. And I'd like to thank you for all your attention, and my colleagues Elizabeth and Joseph for some of the analysis. Thank you.
Oh, there we go.
All right, thank you very much for the opportunity to be here today. So I am at the University of California Pavement Research Center. We're about 85% supporting Caltrans, about 15% supporting Federal Highway Administration and Federal Aviation Administration. I wanted to put our other tiny center up there, City and County Pavement Improvement Center. Anybody here from local government? Okay, local government uses 50% of the asphalt materials in the state, and yet we call them the forgotten 50%. So I think I'm gonna make a few key points I'm gonna bang on today. One of them is local government. Okay, so pavement, who cares? As Tim Greichert said, most people care when they call because there's a problem. We don't get many calls saying, hey, that was a lovely pavement I rode on today or walked on today. Thank you, thank you, thank you. Okay, so in the carbon arena, we're not benchmarked into the sectors, but we cover the sectors that are shown here. We're just finishing a global road network benchmarking for the US DOT, and we'll probably be doing a state-by-state pavement benchmarking for Federal Highway Administration in the next year. But this is our first cut, my first cut a couple years ago. So the biggest factor here is that we influence vehicle fuel use through road roughness. We also influence vehicle life through road roughness. I haven't even put vehicle life, we haven't been able to get funding for that yet, but particularly as we move to electric vehicles, our contribution here will not be that important because it hopefully will be 100% renewable, but we know that vehicle life can be shortened by road roughness. Oil and gas extraction, so asphalt is one of our main materials. So we're in the oil and gas extraction sector, we're in the refinery sector, we're a co-product, we're the low profit carbon, low profit sector of refining. The three biggest refineries in the state have stopped making asphalt. They burn it through pyrolysis. and they don't produce asphalt anymore. But so we're there, and then we use a big chunk of the cement in the state. So that's the sectors we're in. Just doing a first back of the envelope look, our biggest contribution on the state network and the local network, particularly the state network, is out of the, say, 430 million metric tons per year, optimizing smoothness, the emissions that we produce to keep the road smoother through materials and construction, but the savings in vehicle fuel use, we think we can drop it by up to 3 million metric tons per year. If we cut the cement use, maybe 0.2, and if we cut the virgin asphalt use, about 0.7. So a lot of our work is in those materials areas, working on new cement materials, concrete materials, and recycling asphalt and asphalt materials. And then the other one is if we can get roads to last longer, a lot of the damage on roads is hauling out the broken road and hauling in the new materials. So there's a vicious cycle right now. Okay, so 4 key words: full system, complete life cycle. So this is the life cycle of a pavement. It's circular. In the planning area, this is where we look at the environmental, or what I call pavement justice parts of this, both in terms of the impacts and the benefits of good pavement. Pavement rail is pavement. Pedestrian and bike paths are pavement. Asset management, this is one of our biggest areas. This is the programming of preservation, maintenance, rehabilitation, and reconstruction, optimal timing of that, and selection of high-level strategies. Pavement design, figuring out how to use less material or less impactful material to achieve the same life or longer life. Then material sourcing and design. After the design is done, sourcing the materials that we get. Construction, in terms of our specifications for quality control. The largest impact we can have on carbon emissions right now is better construction quality control, to take the investment that we made in the materials and make it last longer so we don't have to replace it as frequently. So construction quality control, another forgotten area, and particularly for local government, through our local government center, construction quality is highly variable. And again, 50% of our major material use. Operations, minimizing work zones, which have some small impact, and then the materials and so on that we use in the preservation, maintenance, and rehabilitation. So we put together a pavement lifecycle assessment framework in 2016 for the Federal Highway Administration. One of the key points, so out of that, we then wrote a state project level program called LCAP, which is currently we're converting it to the Federal Aviation Administration project level lifecycle tool. A key point on this is, well, the top 3 things are data, data, and data. The entire low carbon transportation materials program in California and at the federal level is built on EPDs. EPDs need good data, otherwise, what do those numbers mean? We have 2 sources. We have private providers, cost a lot of money, and they control our use of the data. We're not allowed to let you use our project level tool unless you're Caltrans or UC, because the company we bought that data from has not honored the 2nd and 3rd phases of that contract. So they own us. The public data has no public investment in it. The federal LCA comments, almost no investment. Where I'm gonna advocate right now that you write your congressman. I've met with my congressional staff in Washington to advocate investment through the national laboratories, through the departments, federal departments that are a part of this, to build that database out, because we are standing on feet of clay here with regard to our whole low carbon materials program. Looking at the project delivery life cycle, from planning to network to conceptual design to final design to procurement. Our goal, we wrote a vision for about 20 years ago, is to produce web-based life cycle assessment tools for each stage. This isn't real. I mean, it's not maximum penetration of the market until every person involved in this project delivery cycle, every day as a part of their work flow process, is incorporating this decision-making into it. And they can't do that without tools. So the tools we're looking at are planning level, environmental LCA, and social LCA. We've made beginnings on that. Our main tool is we implemented global warming potential calculation in the pavement management system that Caltrans uses in 2012. They, on their 40-year projections for network level investment in rehabilitation and maintenance, they calculate the cost and they calculate the global warming potential considering both materials and construction and pavement vehicle interaction. So that's integrated in the asset management system. At the design stages, we used our project level tool, which is being implemented by Caltrans. It's probably going to be written into the highway design manual, the thou shalt process that Caltrans engineers and planners use within the next 2 years, I believe. And then EPDs are our tool at the procurement stage. We've written a white paper through the National Center for Sustainable Transportation recommending how to most effectively use EPDs in transportation. So this is a very big diagram, and I hope these slides will be available later. On the right-hand side are each of our web-based tools. So the Caltrans Asset Management System, the Caltrans Concrete and Asphalt Pavement Design Systems, the project-level environmental lifecycle assessment tool, and then we also do the support and coding for the lifecycle cost analysis tool that Caltrans uses. Key point of all of this over on the left-hand side is data, data, data. Who owns the data? Who agrees to cooperate to provide that data, that it's integrated, that it has common definitions, that every time we change data, all the tools that use the same data get updated. And this is where we're at with Caltrans right now, that pretty much we're there. The next step is to integrate the design programs that when you produce the design, it gives you the life cycle cost and the life cycle assessment directly. Right now, you have to go into it as a separate tool. EPDs, right now, everything is built around A1 through A3, which is cradle to gate of the material. That has some issues I'm gonna talk about quickly in just a second, but what we're gonna be working on for Federal Highway Administration shortly is what we call expanded scope EPDs. So we wanna bring in the transportation to the construction site, the construction processes. We wanna bring in the life of the pavement through construction quality standards and be able to model life back into the life cycle global warming potential. And then contractor also controls smoothness so that extra vehicle fuel production, and we want to bring the models that we have in the pavement management system and bring those into the EPD that based on their smoothness, we can account for the improvements in vehicle fuel use while we're still burning fossil fuels. How many are aware of the low carbon transportation materials program coming out, just announced in March, about a month ago? It's $1.2 billion to state DOTs to use low carbon transportation materials based on A1 through A3 EPDs. Once that's done, in a couple months, they're gonna roll it out to local government. And then if there's any money left over, they're gonna roll it back for the second round of state government. We're supporting that through our new National Sustainable and Resilient Pavement Cooperative Center for Federal Highway Administration, supporting industry on setting their benchmark values and then identifying the processes for paying the incentives that will come to them. Performance is incredibly important. As been talked about a couple of folks. This is a typical asphalt mix, and this is a embodied carbon cradle to gate for a typical national asphalt mix, plain Jane asphalt mix, 95% aggregate, 5% binder. The blue part is the asphalt binder, and it is more than 50% of the global warming potential. Asphalt Institute is working on an EPD program right now. Right now we use one number regardless of what the asphalt binder is. So asphalt industry is stepping up, the first sector of the entire oil industry to do that, and there was a little bit of fighting in the corporate boardrooms. So what's the incentive for cradle to gate based on this, reducing our global warming? It's to drop the asphalt binder content. What does that do? It shortens the life of the pavement incredibly. So basically, under the current incentive program, we're gonna get into a situation like this where maybe we have 15% low global warming potential for material A, but it lasts 15 years, and we have a full set of global warming potential for material B. Over a 60-year life cycle, the low carbon material is the high carbon material. This is what we've got to move to performance-related standards for transportation materials. That's what we're working on right now, trying to get that implemented for asphalt, particularly in California right now and across the country. Okay, finally, great talk on supply curves. I've seen them in a couple of the presentations. We strongly advocate this, basically prioritizing what we do. Unfortunately, in pavement world, because not many people know that much about it, what I call crazy, sexy, cool ideas, which we don't know really whether they reduce global warming potential because it's never been quantified and often massive cost, are what are getting prioritized and not the simple nuts and bolts, everyday stuff that we need to do. So I know one of the things we've done, initial study we did, we came up with about $15 per ton of marginal abatement cost for optimizing smoothness. That's a pretty darn low cost of optimizing carbon. Some of the recycling strategies are actually in the negative part, which is where we really want to be. All right, thank you.
All right, thank you for having me. I'm Tommy. I'm up at LBNL, just down the street, I guess. So I think today I'll be kind of talking about, I guess, a synthesis of what all the other presenters really talked about. This is work in progress that's internally funded at the lab. So what we're working on currently is thinking about across the building materials sector, how we can put together different existing LCA models and tools to build a more streamlined tool and integrated tool that works across those different sectors, whether it's transportation, end of life, waste management, production, or other decarbonization technologies, to put it in kind of one place. I don't really need to go through these policies. You've gotten a great background from the other panel members, but a lot of this research is motivated by working with our DOE partners and others to think about how we can support these different buy clean initiatives, EPDs, a range of stakeholders who need analysis support in a lot of different ways to be able to implement these policies successfully. So the key research questions that we're working from is how initially can we set up life cycle models across very diverse supply chains, if we consider regions, communities, different temporal scales, whether we're talking about daily, seasonal, monthly, what emissions change like, and how does that change with different technologies being used at the facilities. Really the driver in a lot of these and a lot of the talks we saw was electricity or energy or processed fuels being mixed, used on site. How do we consider all those different variations across the supply chain and put it all together in one place for building materials? Then thinking through what GHG mitigation actions we could take or interventions to really lower these embodied emissions for a specific building material. Then getting down to what we want to think about is the practical minimum, what's feasible for these different building materials, and really kind of a key aspect to this entire effort is coupling it with a building demand or material demand projection. So using what's out there, some great work at NREL and other places to build out what something looks like for cement or steel or elsewhere in the residential or commercial sector, what that demand looks like, maybe even considering things like demand reduction in design and how that affects our life cycle models within the rest of the model. So kind of visually what that looks like, kind of where we are now is kind of building out those demand projections and also putting together in place this kind of integrated model across the supply chain, considering a lot of different variations. This is really, really difficult when you start to think about building on the research that we saw for something like concrete or pavement or something like that, and getting it down to a regional level or facility level where we're starting to think about different temporal scales or technologies. Then moving forward, thinking about what greenhouse gas mitigation actions can be taken, and then putting this all in one place where we can support policymakers, industry that are putting together EPDs that are trying to make it very accurate and at a facility level. Something so we don't just have the one number that we're seeing for pavement that we just talked about or something like that. And really trying to put this in place so we can implement something like Buy Clean accurately, which, as we just heard in a lot of talks, is really faces a lot of challenges and data, but our kind of goal here is to chip away at the problem, and also while doing that is building a tool that can be used by a lot of different stakeholders. So I'll end it there. I'm not sure, do we have much time? We have a little time, okay.
Thank you so much.
Yeah.
Thank you so much for presenting that. I know these symposia were always compressed for time. There's never enough time to hear from everybody, but we can welcome the panelists back up for a little bit. I'd love to ask a couple questions. I had tons of questions listening to you all. I don't know if anybody is interested in a microphone. You know, just to start off, I heard, you know, a number of folks mention the challenges, the gaps, the big things we need to address. You know, LCA, incredibly ambiguous and data-hungry exercise. I heard, you know, policies. So maybe as you go down, if each of you could just think about, what do you think are the biggest challenges? What is the biggest gap? And you can speak to your sector, or you can think about it for the whole, you know, if you think about your material or otherwise. Anish, I'm gonna start with you, since we're the first.
Okay, sounds good. When I think about challenges for the adoption of low carbon building materials, I think about where they're applied on real projects. So contractors and that really distributed workforce that's using these materials, and the vast gap between rooms like this or rooms where policy is designed and then, you know, the contractor who's applying this material. So education for the workforce, I think, is a major gap.
Yeah, on the concrete and especially the structural side, I think the idea of risk and changing how things used to be done to new ways of doing things is a big challenge. And codes are moving; they're finally moving, and they're moving quite quickly. But I think even, you know, then you have individuals that need to start changing, and that's going to be, I think, the challenging part.
Like, in addition to those challenges mentioned, I want to mention, like, one challenge is like, for like material guy, we shouldn't only like focus on the material itself, but we need to see the whole picture, like how to integrate the performance and how to connect people from the material side, and also structural design, contractor, and everyone together. And of course, this needs like education of, you know, the whole group and community.
Implementation of stronger performance-related standards for concrete and asphalt. $10 million to USDA to convert federal LCA commons into a real database and bring it up to speed. And then an ongoing investment of probably about $10 to $20 million per year to all the national labs and departments, federal departments, to keep federal LCA commons going. And then automation, continued that will bring down the cost of data, that will bring down the cost of of tools.
Wow, I think everybody kind of hit a lot of different great points, and I think it's really just tying all those together in terms of implementation, either whether it's workforce, performance, or funding gaps, or something like that to support data. I think those are all weaving that together to see how it's going to look like in final implementation.
I know we might have time for some questions if anybody. I see hands right away. I'm just going to go for the first one I saw.
This is a question for John. I was astounded at the potential for reducing rolling resistance, and really for reducing rolling resistance in pavements, you know, what that potential impact could be. What is the difference in, you know, with respect to that between asphalt and concrete? Is there a big one between the two materials, or is it all how you
Not a
constructed?
black and white question. That's always the question but that's the question everybody goes to. They both can be smooth, they both can be rough. It is basically, it's true for all of us, if we're born rough, it's hard to get smooth. So it's really construction quality specifications and construction quality, and it's both of them.
Quick follow-up, how about albedo index between the two? Is that something that's, the albedo index between the two?
So albedo is important. We did a whole study on that with Caltrans and Lawrence Berkeley National Laboratory a few years ago. Albedo gets you radiative forcing, acting like a solar ice cap. Changing the albedo of the pavement does not change the embodied carbon, and in fact, our results showed that if we use the reflective coatings, on the order of a 10-fold increase in embodied carbon, because to make them last more than 3 years, they got to be epoxy. So that's not what it's about. The radiative forcing needs better albedo life cycle modeling, and we've done some of that. So.
I know I heard some other hands.
Sorry,
I'm just
but
gonna
very
ask,
important for human thermal comfort on a resilient side. We just want to find out how to do that without high carbon emissions.
there's a cool pavement project right in Davis that you guys got money for. Isn't there a cool pavement project in Davis that they just got funded for too? I have a question. I'm gonna hand this mic up, and maybe for Thomas or, so especially as you're scaling up this rapid tool, do you think there's a danger or a risk in only focusing on greenhouse gas emissions as we scale up and address these big data needs? I mean, aren't we ignoring potential trade-offs then, especially as we push out tools like that?
Oh, for sure. I think that's kind of like the ultimate goal would be to expand it into, local impacts, air quality impacts at a facility level, cost data, specifically when thinking about different decarbonization technologies within the sectors and subsectors. I think that's the grand goal, is to expand the tool into a host of different metrics potentially. But I guess today I just talked about greenhouse gases because that's kind of the easiest one to wrap our brains around right now in building things out.
And it's a decarbonization.
Yeah, I guess that's it. Yeah, it is a decarbonization tool.
People say life cycle assessment, so I feel like it's leading. Definition.
Matt Haig with Cal Portland. Just a couple things. To start off, you don't have to talk about this, but just to put things in perspective on the cement side of the business, like China and the production of cement in China is like, people don't understand, and it needs to be said in meetings like this, that like in the United States, we produce 100 million tons a year of cement. They produce 2 billion tons a year in China. In California, it's 10 million of the 100 million. So I'm not saying all this work is really important, but like we have to keep in mind that globally, like unless things happen on a global scale, what we do here in California is the words drop in a bucket really come to mind. So that's just a comment. And what I'm saying for any policy people in the room is that we need border protections to make sure that cheap offshore high carbon cement don't come into the marketplace. And that's a long-term goal of many of the NGO organizations in our industry in California. But the question I really wanted to get to, you can talk about the first one if you want, but the second one is like, I didn't hear anybody talk about construction aggregates. So we're talking about concrete all day long and the embodied carbon content of concrete, but like the value of high quality aggregates to be able to have an impact on embodied carbon in concrete is massive. Like if you use, I'll say this, crappy rock, you have to add more cement to get to the same strength and durability as you do if you use high quality aggregate. And like no one's talking about what about the availability of construction aggregates to the marketplace. And if anybody wants to talk about that, I think it's a really important subject.
So, sorry.
Oh, no.
On the first point, just spent the last 2 weeks in China talking about EPDs and construction materials. One of our former visiting scholars is working on benchmarking and setting up automated processes for Chinese manufacturers. Otherwise, it's pretty much barely on the radar. I think that will be driven by we're really, as we look at these buy clean policies, we've got to figure out the certification and the quality requirements for the environmental data for imported. Otherwise, it's basically we're going to export jobs, and we're going to increase global warming potential unless we're getting good numbers and they're competing on a fair and transparent playing field. With regard to aggregate, it is like very tiny in terms of the global warming potential of mining aggregate, but we know that across the state on average, we have about 50% of the amount. Everyone in this room is responsible for about 10 tons of aggregate use per year in this state. About 50% of the use to 2050 is permitted right now. It's a 10-year process to get an aggregate quarry permit, and you have about it's about $15 million now, and you have a 50% probability that you actually got a permit at the end of the 10-year process. So what really starts to drive is the A2, which is the transportation, and we've been looking at benchmarking of Florida versus other states, and Florida's asphalt benchmark is up about 3 times the national average, and it's because they have to bring in their aggregate from Georgia and Nova Scotia. So as we're moving to aggregate importation, we're going to start driving that. That's going to become an increasingly larger driver. Right now, mining it in state is almost nothing, but it's the transportation that's the big dog.
I have a question, if I may. So I was hoping you could speak a little bit to the recarbonization of concrete, or the carbon uptake of concrete pavements, and how that impacts the total LCA throughout a concrete pavement's life.
So one of Sabby's, do you want?
Yeah, maybe Jen or.
Oh, there you go. Yeah.
So for the recarbonization of concrete, it's how we utilize it. It depends on several, like parameters we want to consider. For example, like how long do we, like where do we want to dispose it or storage it, or like how like fine we want to crush the concrete. It have different rate of carbonization. And the energy grid we use, all kind of stuff, we do have analysis of that, but yeah, it totally depends on.
And it's like what percentage? About 20%? 10, 20% recovery?
I don't know. It is really variable, but.
For pavements, I mean, that's fairly consistent?
We don't really know yet. It's probably, if you just use fixed law of diffusion and everything was optimal, maybe 15%, it depends-ish. I'm just throwing out rough order numbers here, but we don't really know how fine you have to crush it, humidity conditions, exposure to air conditions, how long, what are the rates. It's an area of research. One of Sabi's students actually working on this right now, if she's here.
There's also a poster on it. And the added issue is that the emissions tied to cement production happen in a pulse right at the beginning of the cement life cycle, right? We emit a bunch of CO2. And then the hydrated cement does slowly absorb a little bit of CO2 during the life, but the surface area isn't really that immense relative to the volume. So what everyone's talking about is actually the end of life, right? Crushing it, getting a good surface area to volume ratio, but that's like decades later. So we've already sent the CO2 into the atmosphere. It's already contributing to cumulative radiative forcing, and the uptake ends up being not only like less than the emissions, but also further into the future. So the net effect ends up being relatively small.
On a paving surface that's, let's say, maybe ground 2, 3, 5 times throughout its life?
You're maybe on a pavement, you're maybe going to carbonize over 40 years, maybe.
Just a
First order estimates on a 40-year life of a concrete pavement, although they often last longer. You're talking some few millimeters of the surface. If it's good concrete, because if it's air permeable, it's not going to last very long. So, so the bottom line in our mind right now is don't count on that right now. We need to do better research. It's one of the third and fourth order things that we should be focusing on. Build the data, build the models, and then we can start to bring it into our tools. But right now, we don't even know if somebody's going to have the cost ability and the time ability to actually even make it happen.
Sorry to interrupt, but like most of a lot of construction is happening in urban areas now, like LA, in a city, think about it. Like, so when you build a new building, you often have to replace it. You're replacing a building. So I would argue that in those cases, I agree with Sabby's point that like you pour concrete today, it doesn't come out of the ground for 40 years, right? But in a lot of cases, you are destroying a structure, crushing it up, and that's when you open up the potential for carbonation, and a lot occurs. So I think there are a lot of cases in these sort of urban areas where carbonation should be studied and perhaps accounted for when you're replacing structures.
We're studying it. It's a potential for that expanded scope EPD thing that we're looking at. And what we're trying to identify is a threshold of confidence in the data and the models, and also who controls that process and will they actually make it happen? That's maybe it happens, maybe it doesn't, maybe it gets buried, you know. How do we certify that it will actually happen and we can count on it?
It's fascinating, both problems obviously from a standards perspective with respect to, how do we assess these things? And then also on the data perspective, we don't always have the data and we still have a lot of work to do. So I really want to thank the panel. Really excellent discussion. I know we could have gone for another hour. Let's give them a round of applause.